Hello everyone, my name is Devendra Kapadia and I'm the manager of Mathematical Computation at Wolfram. On behalf of the WolframU team and the Wolfram R&D team, it's a great pleasure to welcome you to this webinar on mathematical computation in 14.2. Now, mathematical computation is a vast area of the Wolfram language, and in this one slide over here, I'm going to capture the new release. So we have two rows over there. The first row is the new and exciting features which you're going to hear about today. And the second row over here is calculus, which is in a sense our bread and butter. And we strive to maintain our almost 40-year lead in this area. So as regards today's webinar, we'll begin with game theory, a brand new feature where we have so-called matrix games, tree games, lots of built-in games, and this is a new territory that we've conquered for release. It all began with a problem in polynomial equation solving, the problem of finding Nash equilibria, and that was solved, and we took it from there, and we built this nice framework for game theory, which you'll hear Mark Vicuna talking about in just a short while. Mark is a young computer scientist, a statistician, and even a philosopher. So he's someone who's represents a modern view on things. I encourage you to ask him questions as we go along during his talk and later. So that's the first talk for today on game theory. The other big feature is array algebra. Array calculus and algebra is the big thing from 14.1 and 14.2, and we have an expert, Adam Strasbonsky, who will present it. He is the developer for the new function 14.2, array expand, array simplify, and component expand. And this actually fulfills a promise we have made to our users maybe 30 years ago. It just proved very daunting, but now we've done it. And so simple things like this identity from linear algebra now become possible with the new release. So I think we're adding a layer of abstraction which has been lacking for a long, long time. And finally, I want to get to a feature that people love, and it's to do with PDE modeling. Now, PDEs are themselves interesting. Real-world modeling has got its own charm, and then there's geometry. So that's kind of a heady mixture, and you'll see Oliver Rubin Koenig presenting PDE models in magnetic fields. So it's the kind of thing that we've done at high school or middle school with magnets and filings now becomes possible by real-world modeling. That's a great achievement. And the Maxwell equations themselves are so beautiful. So I think Oliver is a great person to interact with, to ask him, Adam and Mark questions as you go along. But I think that the brand new feature, magnetic field modeling, is truly wonderful for this release. So that's for today's webinar. But then there are things we won't talk about in a lot of detail, but there is the support for vector variables in several calculus functions like surface integrate over here. So you can use purely vector variables. That's not really an economy, but it kind of gives more insight into what's going on. So it's a continuation of the project that Adam is going to present today. But I think this is a road that we won't take. Maybe in future we might have it for more applied areas like control systems, etc. But if you have a suggestion, let us know. We've just finished a long program to develop Laplace transforms, almost 5 years of hard work on it. And then we released a course a few weeks ago. And next week, we actually have a study group on Laplace transforms with hopefully a draft textbook for you to learn from. So Laplace transform is kind of done from our angle, but the next thing is Fourier transforms. We began in 14.2 with some very nice documentation updates, like the table you see over here from a typical textbook. And we hope to go down the Fourier transform road just as they've done for Laplace transform. But I think that's another core calculus update, Fourier transform documentation, and a few other improvements. And finally, there's much talk about generative AI and AI in general, but and people kind of wonder at the new capabilities. But honestly, there's nothing new for us. We've had Wolfram Alpha for a long time, the best math AI in the world, And when Wolfram Alpha began, I was surprised to see that a function called sum convergence that I wrote in 2007 actually suddenly became very popular because students like to test convergence of infinite series for their calculus classes. And so over a period of time, we made lots of improvements. And recently, the Wolfram Alpha team asked me to make an improvement whereby we'd allow the interval of summation to be part of convergence testing. So you've got two examples over here, 1 over n square. But in the first case, when you were 0, you hit a singularity, so you get back a false. And here you got no singularity, so you get back a true. That's of course just the convergence corresponding to the Riemann zeta function, zeta 2. So we got a really nice mix of things. We'll focus on new features, but the point of such webinars is to give you a chance to ask us questions, give suggestions, make comments, and those really do encourage us a lot. I do pass all your feedback to the R&D director. So I'm going to quickly hand over to the team for presenting their talks. But I should also mention that we have, in addition to the speakers and myself, we have Lewis Britton from the Wolfram Technology Group. Lewis is a great resource for answering questions from people like you. So do ask questions, not just related to today's topics, but anything in general about Wolfram. And we also have Roberto Martinez in the background, who's going to do all the hard work of keeping things going. So we have a really good plan for you today. And maybe it's time for me to stop and let you enjoy the first talk by Mark Vicuna on game theory. Thank you very much for being here.
So, what's new in 14.2? Hi, I'm Mark Vicuna, one of the main developers for the new suite of game theory functions coming out with Wolfram's 14.2 release. So, what is game theory? Is it a theory about finding optimal game strategies? The mathematical analysis of competition? A process by which mathematicians take a simple game of tic-tac-toe, ruin the fun of it, and transform it into a huge tree structure? Well, those are all part of the answer. But what is game theory really? I would argue game theory is the mathematics of decision making. Whether you're thinking of your next chess move or choosing your answer to an opposing political candidate, you are taking a decision that will affect others' decisions and that will ultimately benefit or detriment all parties to varying degrees. Of course, it would be a mathematical crime to talk about game theory without embracing its roots in actual recreational games. In terms of history, initially, mathematicians like Girolamo Cardano and James Waldegrave studied games to win bets and discover better game strategies. You know, the good old days, when the player could actually be smarter than the house and ruin gamblers with more than just luck. Eventually, economists like Antoine Augustin Cournois and John von Neumann extended these ideas to all forms of decisions, particularly economic decisions. Game theory officially starts with John von Neumann's 1944 book, Theory of Games and Economic Behavior, where the term game theory was coined and the axioms of game theory were determined, establishing it as its own field. It's a major shift in scale. When a game can be as big as an economy, players are not necessarily human. Monopolies, governments, corporations, and many other institutions can also be players. In this context, the idea of a payoff is quite literal. Corporations will most likely prioritize financial gain and minimized costs, leading to predictable actions. Nowadays, game theory is about competition cooperation, diffusion, and stabilization of behaviors in biology, robotics, and much more. Hunting patterns, migration, and many more animal behaviors can be explained through game theory. These behaviors may also be simulated through intelligent agents, better known as bots, who constitute another large area of research for game theory, multi-agent systems. So Wolfram's game theory functionality can be divided in three major parts: matrix games, tree games, and game theory data. Let's start with matrix games, also known as simultaneous games. Game theory often seems meaningless without examples. So let's take me as an example. My wife and I would like to get a pet. However, I know she prefers dogs and she knows I prefer cats. For Christmas, each of us choose to wish for either a dog or a cat. These are simultaneous decisions. Now we can combine those decisions in a matrix game in the following way. Before I explain my choices, let's also visualize it as either a dataset or using the matrix game plot function. Okay, so we have a better view of things. Here, if we both choose dogs, I'll be happy to have a pet, and she'll be even happier because she has the pet she wanted. If we both choose cats, she'll be happy to have a pet, and I'll be the happier one because that's the pet I wanted. However, if we choose different pets, we'll have to get both pets, and we both hate the idea of having a dog and a cat simultaneously in the house. So what do you think we should do? Any guesses? We can use fine matrix game strategies to get us the Nash equilibria, which can be seen as a set of decisions where all players can't individually improve. Here we can see three different strategies. We could both choose to have a cat, we could both choose to have a dog, or we could both choose a cat or a dog depending on some probability, which equalizes our expected payoffs. We can use matrix game payoff to see the expected payoffs. As you can see, the equalized strategy is far worse for both players, so it makes sense for us to agree on the pet we'll put down in our list. But to me, that doesn't really solve the issue. It feels like we're back at square one, having to choose between dogs and cats. So as a game theorist, I'll change the game a bit. Tree games are also called sequential games, as players take actions sequentially. Again, we both have the choice between writing down dog or cat. However, when I combine choices in a tree game, I have to order them sequentially. Again, let's create a game combining those decisions, and let's visualize it. In this tree game, I choose first between a cat and a dog. I then show my wish list so that my choice is known. Then, it is up to my wife to choose between a dog or a cat. Find tree game strategies allows us to find the subgame perfect equilibrium, which can be seen as the Nash equilibrium of tree games. In this case, the strategy proposed is for me to choose cat, and for her to choose dog if I choose dog, and cat if I choose cat. This corresponds to the expected payoffs of 2-1 in my favor, using the tree game payoff function. Clearly, this formulation of the game advantages the first player to act. So you now have a basic grasp of game theory in 14.2. Thankfully, most of the remaining functionality is designed to take your understanding of game theory to the next level. Starting with game theory data, the function has 49 different well-known games that you will encounter when studying game theory. More than just a fixed game, game theory data gives you access to the classes, the description, and the source of each game. Many of these games can be extended to n players, such as this Dinner's Dilemma extended to 6 players. This functionality should enable you to dig deeper and learn while playing with the data. Game theory data also contains more exotic games, with properties going far beyond what I could explain in a single talk. This deep functionality is paired with fine-tuned documentation to enable learning and usability, where all the details of these new objects are explained simply enough for anyone to appreciate and use game theory. The examples follow simple workflows applicable to any game theory tasks. Understand the game, generate it, visualize it, and solve it. The game theory documentation has a lot of these workflows, with almost every game documented with examples and explanations. Of course, all the game theory concepts that were explained in this presentation and much more are explained in the documentation. So what would it actually look like when you'll visit our documentation? Here's the guide page, and so you should have a better idea of exactly what to expect. So as mentioned, first we have matrix games, and second we have tree games. And so for each of those types of games, you have the object itself, which for matrix games implies that any simultaneous game can be expressed as a large matrix. And so you see that matrix structure over here. And for tree games, any game follows the tree structure. And so there's nesting in each of those actions, possibly, which follows the same kind of nesting you would see in a tree. So coming back to the functions, each of those games have plotting functions, matrix game plot and tree game plot. Matrix game plot takes a matrix game as input and a strategy also. Same for tree game plot. It takes a tree game and a tree game with a strategy. Then we have a solving function, find matrix game strategies to find the Nash equilibria, and find tree game strategies to find the subgame perfect equilibria. So we have the matrix game and the specifications. It's worth mentioning that those functions have methods that could be find instance and solve values. You could see find matrix game strategies as an application of our state-of-the-art polynomial solving. So find tree game strategies is a bit different. This relies on backward induction, so this solver is a bit simpler. Then for each of those functions, we have verify matrix game strategy and verify tree game strategy to verify if any of those strategies are indeed a Nash equilibria. It turns out that this computation is much simpler than the solver, so it's very useful to verify any of those. So it's very useful if you ever want to try to guess optimal strategies, make your own searching algorithm for the Nash equilibrium. Same for verify tree game strategy. Then we have matrix game payoff and tree game payoff. For matrix game payoff, we have different properties, such as, of course, the expectation, but also marginal distributions, multivariate distribution, simulation, variance. As for the tree game payoff, we have different types of adversaries. These allow you to assume some actions are done by either perfect or random players, and therefore it allows you to play games against players. We have two new options, game action labels and game player labels, if you want to label the actions or the players. And of course, our big game theory data, which covers all the predefined games. All right, thank you for listening.
Hello, my name is Adam Strzeboński, and today I will be talking about calculus and algebra with symbolic arrays. So symbolic arrays have been introduced in Mathematica 14.1 and 14.2. In Mathematica 14.1, we have introduced non-threadable attribute. This is a new attribute that prevents threading of listable functions. It is given to symbols that may be used to construct expressions that represent arrays. So let's look what are the current symbols that have the attribute. So basically, these are functions that give arrays as output. Also in version 14.1, we've introduced symbolic array variables, vector symbol, matrix symbols, and array symbol. Special arrays, 4 types of special arrays, symbolic, and we've implemented symbolic array calculus. So D now works with symbolic array functions and symbolic array variables. In Mathematica 14.2, we have added symbolic array transformations. So these are 3 new functions: array expand, array simplify, and component expand, and functions tensor expand and tensor reduced have been updated. So let me start with symbolic array variables and threading. So a long-standing difficulty with using symbolic vector, matrix, and array variables was that evaluation of arithmetic operation treated symbolic expressions as scalars and threaded them into list arguments. So for instance, if we add x to a list, x gets threaded into list elements. So if we would like to set up a convex optimization constraint a dot x plus b vector greater or equal 0, because of threading, we were not able to do it directly. So as you can see, x here is supposed to represent a vector, but it was threaded inside the dot product of matrix, and the vector was threaded inside the vector b, so we didn't get the correct form of the inequality. So as suggested in the documentation of convex optimization, we need to use inactive plus here. So if we use inactive plus, then we could set this constraint and convex optimization would work with it correctly, though it was slightly inconvenient to have this inactive plus here. instead of just typing the plus and have a live expression. So in Mathematica 14.1, we have introduced a new threadable attribute that specifies that a symbol, along with expressions that have this symbol as the head, should be not threaded into lists. So they are treated as representing array variables. So we set attribute to a symbol sim, and now it does not get threaded into the list. Also, the same thing with an expression which has sim as a head. So most standard built-in functions that produce array results now have the non-threadable attribute. So if we take inverse of mat, that's supposed to represent a matrix, so it will not thread into an explicit list matrix. And expressions obtained by applying listable functions to non-threadable objects are also non-threadable. So for instance, this expression cross UV is expected to be a vector. Then we apply sign, it's still a vector. So if we add some object W, it will never be a scalar. So this is implemented using non-threadable expression flag. So we can use the internal function to check that this expression indeed has non-threadable flag. And in fact, this expression will not thread. So if we multiply it by a list, it will not go inside the list. Symbolic array variables. So we have introduced 3 new symbols that can be used to represent array variables. So vector symbol, matrix symbol, and array symbols are new objects that can be used for symbolic representation of vectors, matrices, and arrays. So for instance, this defines a vector symbol with dimension 2, and we can look at the tooltip. It will tell us that it's a vector symbol and it has dimension 2. But it's represented just in traditional vector representation. So the new objects have the non-threadable attribute, so adding vectors to an explicit list vector will not thread. And now we can set up the convex optimization problem directly. So you can see this dot product did not thread into the list, so we got the vector inequality in the correct form, and we can use convex optimization to solve the problem. And array variables can be used in other solvers. So for instance, let's define a matrix variable. It's a 2 by 2 matrix. We can also look at the tooltip to see the dimensions. And now we can solve a system of equations for the matrix variable. Or here, this produces a depth 3 array, 2 by 2 by 2, and we can minimize trace of this array, and here's the minimum. So symbolic array expression. So here, this represents a matrix with symbolic dimensions m and n. Now we can construct a symbolic array expression. So we use array operations, use transpose, conjugate transpose. Here's the expression. And we have nice typesetting for it, traditional. And we can compute the dimensions of the result. So it's m by m by n by n array. So this represents an array of depth 3 with symbolic dimensions PQR. So now if we subtract A from A, it's an array symbol. So the result should be arrays of zeros rather than just 0. And indeed, our arithmetic functions know that. So the result is symbolic 0 array. Symbolic zeros array represents an array of zeros with dimensions p, q, and r. If we add 1 to symbolic zeros array, we get symbolic ones array. And if we specify numeric expressions, numeric dimensions of this array, normal will produce the explicit list array. So here is the array of ones with specified values for p, q, and r. Array derivatives. So in version 14.1, we have introduced derivatives of array valued functions with respect to array valued variables. So for instance, let's define A to be a matrix symbol, V to be a vector symbol. Now we take a derivative of a vector valued function. So it's a matrix dot vector, so it's a vector valued function of a scalar variable. So D assumes that if X was not defined as an array variable, it's a scalar variable. And here's the result. And here is the derivative of a vector valued function with respect to a vector variable. So A dot V with respect to V. And here is the result. The result is the matrix A. And derivative of the same function with respect to matrix variable now. So it's an identity, symbolic identity array dot vector V, and this is a new transposition format. This means transpose by rotating dimensions by 1. And the dimensions of this are n by n by n. We can compute it with tensor dimensions. So this was a vector valued function. So the first n corresponds to the values, and the two n's correspond to the dimensions of the variable. So symbolic identity array here has been used is the result of differentiating an array variable with dimension dims with respect to itself. So if we take derivative of array variable with respect to itself, we get symbolic identity array with dimensions n by n. So it's the actual tensor dimensions of this are n by n by n by n 4 times. So it's 2 dimensions due to value of the function and 2 dimensions due to the variable. Here is a derivative of a matrix valued function with respect to a matrix variable. Again, the result uses symbolic identity array and the transpose in this new format by rotating dimensions. Another special array used to represent derivative is symbolic delta product array. So that's something that will appear in the derivative of total of A with respect to A. So this is the n by n by n array such that its ijkth element is Kronecker delta of ik. So for instance, we can check this for n equals 7. Normal would produce the actual array, and it's indeed equal to table of Kronecker deltas. Now we can also specify the domain of a vector variable. So if we give the third argument to vector symbol, this specifies the domain of the vector. So this is a real vector length n, and variance is differentiable only for real vectors. So we actually needed to use real vector symbol to get the result here. Now let's talk about chain rule and array dot. derivative of a composition of symbolic array-valued function with respect to array variables. So we take matrix symbol m by n, array symbol pqr, and vector symbol v, and we take matrix valued function of array valued function of a vector, and we take derivative with respect to the vector. And here is what it is. It looks very similar to the regular chain rule, except that instead of multiplication here, we have array dot. So we look at this, it's array dot of this first derivative of f of g, and then first derivative of g of v. And this says that it's a three-dimensional array dot. So array dot computes the product of arrays a and b obtained by summing up products of terms over the last k dimensions of a and the first k dimensions of b. So regular dot is in particular would be array dot, comma 1. So let's see the tensor dimension of derivative of f of g is a depth 5 tensor. This corresponds to f, this corresponds to g. Then tensor dimensions of derivative of g valued at f has depth 4. These are 3 dimensions corresponding to g and the dimension corresponding to v. And so tensor dimensions of g will be, we sum up along these dimensions, so they will be mn and k. And the tensor dimension gives us this. So let us show an example. Taylor approximation. So we find the first 3 terms of the Taylor series of inverse A at point C equal to identity matrix of dimension n. So A is a matrix symbol. We take F to be inverse of A, and C is a symbolic identity array of n. So the first term of the Taylor series is just evaluation at the center. So here it is, inverse of symbolic identity matrix. We can simplify the result with array simplify. This is a new function in Mathematica 14.2. So the first term is, as one might expect, identity matrix, the inverse of identity matrix, identity matrix. The second term will be f prime of c, array dot over 2 dimensions of a minus c. So that looks quite similar to what it is for Taylor series of scalar functions, except that we have array dot here. And here is the result. Now let's simplify it and dot it with a minus c. Here we got quite nice simplification of this formula. And the third term is 1/2 of second derivative dotted with a minus c twice. So here is the result. Quite large expression. We can get it simplified to slightly smaller form using array simplify. And now let's compare order 0, 1, and 2 Taylor approximations for n equals 7 and a with random entries within 10 to the minus 10th of the 8 entries of the identity matrix. So here is the 0th order approximation. As one might expect, it's up to 10 to the minus 10th. Now, first order approximation approximates the value up to 10 to minus 20, and third order approximation up to 10 to minus 30. Another new function in Mathematica 14.2 is array expand, which expands out symbolic array operations. The function makes use of multilinearity of array operations, as well as of numerous array, matrix, and vector operation identities. So here is the kind of obvious linear expansion of dot with respect to plus. Out here are a few other examples of expansion. So it's trace of linear combination. We have to specify that S and T are scalars. We do it with an assumption that S and T are complex numbers. And here is the expansion. Here is the expansion of inverse of dot of two arrays. Here we of two matrices. Here we specified that A and B are matrices using matrix symbol. Here is expand of transpose of dot. And now we specified that A and B are matrices using the assumption. So there are two alternative ways of specifying that the variable is a matrix. We can do it with matrix symbol or by specifying it with an assumption. And here's an expansion of determinant of 3 times a matrix. See, because matrix symbol has built-in dimension, we could use the dimension n here and get this result. And here's a slightly more complicated expand of dot of cross. Now another example, formula derivation. So we derive a formula for the gradient of the least square cost function. It's an example from Mathematica Stack Exchange Post. So here, let's define x to be a matrix, y to be a vector, and theta to be a vector. Define the cost function. Compute the gradient. And it came out slightly more complicated in a book on the subject, but we can use array expand to simplify it, and we get exactly the requested book formula. Another example, we can prove linear algebra facts using array simplify. So we define u and v to be vectors and a and b to be scalars. We can encode scalar of as an array symbol with empty list of dimensions. And what we are proving here that any linear combination of 3D vectors is orthogonal to their cross product. So we take cross product and dot it with a linear combination of vectors. And now we can simplify it and we get 0. So indeed, we have proven that it's orthogonal. Another thing we prove here is that determinant and trace are invariant under matrix similarity. So we define 2 matrix symbol and matrix B is a matrix similar to A using the matrix P. And we can simplify determinant and trace of B, and they are determinants of and trace of A. So it's indeed matrix similarity doesn't change determinant and trace. Finally, we have another new function in Mathematica 14.2. It's component expand. Component expand expands out symbolic array expressions in terms of indexed components. So this gives us a vector as a list of components. Here is a matrix expression, determinant expanded. Oh, okay, now we need to clear A and B. Otherwise, we are getting something strange. So here it is. With symbolic A and B, we take the determinant of A dot B, expanded in terms of coordinates. And here is expansion of a vector inequality in terms of coordinates. And finally, an expression that's dot product of symbolic ones array and a matrix symbol. And this was the last example. Thank you for listening.
Thank you. Okay, my name is Oliver, and I work mostly on numerics, PDE modeling, and the finite element method. And I'm going to be presenting about new functionality in version 14.2. So before we start, I'd like to point you to the finite element core area page. That's a web page. You can Google that. And the nice thing about this page is it gives you a pretty good overview of what type of things we can do with the finite element method and PDE modeling generally. So if you're new to this area, you can have a look at this page. It talks a bit about geometric modeling, how to make the geometries, mesh generation, some fields of physics like heat transfer, fluid dynamics, mass transport, solid mechanics, acoustics, things like that. Electromagnetics, we're going to be talking about that quite a bit today. Yeah, multi-physics, system physics, and things like that. So if you want to get an idea of what type of things we can do, the webpage is a good place to start. Okay, so the most important slide of my presentation is probably this, and that's because it has a link to the reference pages or to the documentation that gives you an overview of the examples and documentation we have for this. It's called the PDE models overview page. We can have a quick look at that page, page. So this is in the help system, gives a short introduction. And then again, all these fields of physics that we've seen on the web page are also mentioned here: acoustics, electromagnetics, fluid dynamics, etc., physics, structural mechanics. So, and these pages are always organized in the same way. So you have the initial thing is a guide page. It talks about the functions that are available, talks a bit about the monographs that are available, the models that we have. And maybe one last thing is, so if you want to do, for example, heat transfer, you're looking for a 3D example, you can look at this list and say, okay, Joule heating, laser welding, and this multi-layer heat transfer, those are 3D examples. You could look at those to get a start. So going back to this PDE models overview page, the second thing is usually the monograph or monographs. In some cases, we have several. And so, I don't know, if you're interested in volumetric heat transfer, you can go there, and it talks about the theory about this. It gives examples how to use the functionality to model these type of things. Yeah. Then in some cases, we have verification tests. That's basically tests from books where we have analytical results and things like that. And they show that the solvers that we've set up do the job they're supposed to do. And you can convince yourself that they do that just fine. The next thing is the model section, and those are really examples, like more extensive examples that you typically find in the reference pages of the things. So if you look, for example, at the heat exchanger, it has a short introduction, gives a graphic of what's going about, talks a bit about the model, lots of discussion, how to create the boundary conditions, the models, and things like that. So these are explained in quite a bit of detail, and they are supposed to be real-world examples. So it's not a simple like two-line solution. And the last item here is examples, and those are examples from the standard reference pages that are a bit more elaborate. So you can I mean, those are the examples I just thought worthwhile mentioning here, because they go a bit beyond what typical reference page examples do. But again, of course, reference pages, looking at those is also very, very useful. One thing to keep in mind is, so if you didn't see your favorite field of physics that you work in, that doesn't mean that we cannot solve these type of PDEs. It just means that we don't have any prepackaged functions or monographs accompanying those functions. But you still might very well be able to solve a specific problem, just so that you know that. Okay, so version 14.2. The things that happened there are we did some updates in the Open Cascade link. Open Cascade is a 3D CAD engine that we use in some aspects to do our 3D modeling. And we've now updated or continue to update the drafting mechanism. Drafting means that you use 1D and 2D lines and combine these 2D objects into a basic draft that you can then extrude into 3D. So we've worked on that a bit, and that provides new functionality. And if you click the link in the presentation, you will be able to see what exactly that is. In solid mechanics, we updated the plane strain and plane stress cases to an extended plane strain and extended plane stress case. And extended means that even though the plane strain and stress case are 2D models, they do have values in the third and the z direction. And previously, you could either manually compute that component, or you could use a little bit of a hidden function, but now these are fully exposed, and the extended plane stress and extended plane strain provide you with values in all three directions. Electromagnetics is a new component in version 14.2, and we're going to talk a lot about that today. So we have new components there, and the last thing I'm going to be showing is a new finite element update that I think is worthwhile mentioning. All right. So electromagnetics. In version 14.0, we started off with electrostatics. Version 14.1 had a new monograph, that means a function and a monograph. And in version 14.1, we had the electromagnetics overview monograph and the electric currents component that were added. And in version 14.2, we've added functionality magnetostatics for permanent magnets and quasistatic magnetic fields. So these two are the new contributions for 14.2. Now, so electromagnetics is based on Maxwell's equations, and while they're very beautiful, they're also very complicated to solve if you want to solve them in their full extent. So many of the electromagnetic applications try to make sensible simplifications such that the solution time and the solution, basically the solution resources you need, like time, memory of the computer, are reduced. So we have simplifying assumptions to reduce these. And all these assumptions that we've used to extract specific things like the magnetostatic case or the electrostatic case or electric currents are explained in the monographs. But here we have a small, like an overview, a chart that allows you to decide what type of equation you should be using. So if we're looking at electromagnetic modeling, the first thing to ask, is this a transient, a time dependence problem or not? And if it's not, we know that the time derivative of the E and the B field are 0. Then we can decide, do we only look at the electric field or only at the magnetic field? If we have the electric field, we can decide what constitutive relation we want, and we might get to the electrostatic PD component or the electric current PD component. Now, in version 14.2, we've added these components, so the magnetostatic PD component and the magnetic PDE component. And that covers basically all non-transient cases. For the time-dependent case, you typically look a little bit at the size of the object compared to the wavelengths. And if that size of the object is smaller to the wavelength, we're in a low frequency, in a quasi-static state. Then we decide a bit what the skin depth has to say. And if the skin depth is larger than the object, then we have an electric current PD component that helps you to solve these type of problems. And if we have a skin depth that's smaller than the object size, we compute the E and B field, and the magnetic PD component will be able to help you with that. What we don't yet have is the high frequency component. So the full electromagnetic wave PD component, that's reserved for a future version. Again, you can solve this today, but we just don't have a prepackaged function for this. So with 14.2, we basically everything except this electromagnetic wave PD component is available for electromagnetic modeling. Okay, so let's continue a bit here. Right, magnetostatics. So again, there is a guide page with the boundary condition and the function names. The function is a magnetostatic PD component. The boundary condition is the magnetic potential condition and the magnetic current density value. We can use this function in 1D, 2D, 2D axis symmetric, and 3D models. It's a stationary model. You can create a time-dependent model of it, but it's not quite sure what you'd use it for. It's a magnetostatic case. And the dependent variable is this vector potential Vm. It's a magnetic potential. That's the dependent variable. It's a scalar variable. It's a scalar equation. And the important thing is magnetostatics is always set to 0, so you don't have any external currents. We'll get to that in a second, or in a few minutes, actually. All right, here's an example. So we load this pre-made geometry of the permanent magnet. So we have an iron coin, or actually this is only a quarter of the entire geometry. So you'll imagine this part is reflected, and to the bottom, we also have an extent. And we import this geometry. So this was created with the Open Cascade. And in the documentation, you'll find exactly how we've done this. So you can have a look at that too. So we'll import that geometry. Next thing is I generate the finite element mesh, and for that I set up region markers. So region 1 is this iron coin, that's this part. Region 2 is this part here, is the iron, and region 3 is the magnet part, this is front part, and the surrounding is air. So I generate a finite element mesh with the region markers giving a point in these specific regions, and then these markers will be distributed. We'll see in a second what they're for. And this generates a mesh, a tetrahedral mesh of 15,000 elements. All right, so now this is the PDE we want to solve. So we set up the variables. So it's the magnetic vector potential, and X, Y, Z are the independent variables. The parameters, we start with an empty list. We set the relative permeability to 5,000, and the element marker is the region marker of the coin or the iron, and all other cases have a relative permeability of 1. We set a magnetization vector, and the magnetization is in the region magnet. The element marker is the magnet, and we set 800,000 ampere per meter. And the magnetostatic PD component will then generate the PDE, or the PD component. Next, we set up the boundary condition. We have an antisymmetric plane. So at this y equals 0 plane, we have an antisymmetry, and a magnetic potential condition can be used to set this antisymmetric plane. It's a Dirichlet condition on the vector potential is set to be 0 on this plane. Now we've got everything together, and we can use and dissolve to compute the solution. This will return us an interpolating function. That interpolating function is transformed into a discontinuous interpolating function, and that means that when you have multiple material regions, you will get nice, sharp, and crisp interfaces at these material boundaries. So that's what this discontinuous interpolating function is for. We've introduced it in 14.0, and if you click on the link, you'll get to the documentation of that function, what exactly it does and how it works. To compute the B field, we compute the negative gradient of this vector potential function. We extract the relative permeability, set mu0, and the magnetization. And then we evaluate the B field on the element mesh by evaluating this formula on the mesh. And then we can visualize the B field of this permanent magnet with a coin in front. Okay, So far, so good. So this was magnetostatics, and I still wanted to talk a bit about the quasi-static case. So now we have a vector-valued equation. So we have the magnetic vector-valued potential. The function that generates the equation is the magnetic PDE component, and we have a magnetic potential condition. We can do this in 2D and 2D axisymmetric models. You can also use this for 3D. There, however, setting up the boundary conditions can become a bit tricky, but in principle it's doable. But I just want to mention that it's not. You'll have to think a bit about the boundary conditions, but it's possible. And here is the function where we can have external currents. So if you ever have any magnetic cases with external currents, you use the quasi-static magnetics case. And we're going to look at an example. So this is an electric motor. So we have a stator, we have coils, we have a rotor, and we have some material air. What I have here is the H field and the B field magnet data. That's plotted here. I normalized this the B field by the H field basically. So I call this mu data, and then the BH data is the transpose. So that's it's a list, a pair of values together. From this, I generate an interpolating function, BH data. The interpolation order is 2, and I've added an extrapolation handler. So this extrapolation handler is a way to specify how the interpolating function should behave if it's queried outside of the data. So if the query value is smaller than the first value in this B field list, then I want to always return the value at that first point. And if it's larger, I want to return the value of the last field, of the last data point in this field. And I don't want to see a warning message when it's queried outside. All right, so now we'll set this up. So we'll have the AX and the AY component are set to 0. We want the AZ component, so the field in the Z direction. We specify the norm of the B field is the gradient, the square root of the total of the gradient of the AZ component. I've added a small machine epsilon here, and that's because when the symbolic Jacobi derivation is started, we'll get expressions that have 1 over the B norm. And in order to avoid this not to get to 0, I've added a small number. It's not going to affect the solution in any way, but it avoids this to get to 0. So that's why this machine epsilon is here. And we set up mu0 and mu r, and that's now the interpolating function evaluated at the norm of the B field divided by mu0, and when these element markers are true. So this is in the coils. No, this is in the, let me see. Let me go back. Right, it's in this data here. Yeah, okay. So now we have the J0. That's the current that's in the coils. So element marker 4 and 6 are the coils. We have a positive value in one direction and a negative value of 10 in the other direction. We set up the parameters, generate the magnetic PDE component. That's generating the PDE. We have the magnetic potential condition outside at the outer rim, and we get a solution in the AZ direction, and we again transform this into a discontinuous interpolating function. Last thing that remains is to compute the B field, and this is the curl of this component in the Z direction, and there you have the B field of this motor example. Okay, so I also want to quickly mention new application examples. So the one that's interesting that's related to magnetic fields is inductive heating. So this couples electromagnetism with the heat transfer module. So you can combine these two things. And in the previous version, that's a bit of a different topic. We had a cerebral aneurysm computation. And for this version, we've made this a time-dependent cerebral aneurysm computation. So it computes non-Newtonian fluid flow through this aneurysm, and we make a prediction of the rupture site for this aneurysm. So fluid dynamics, different topic, but this is really a cool example. I wanted to mention that. All right, so the FEM update I wanted to give that I thought was worthwhile mentioning is, in this example, I've created some data, some sine data for time, and create an interpolating function from this, ifun. And I also generate a second order PDE, second order in, so it's an X and Y component. And the interpolating function is in T. So it's not a spatial interpolating function, but a time interpolating function. And the new thing is that this is now much more efficient than it was previously. Previously, the evaluation of this was fairly expensive, or was more expensive. So if we now solve this component here, it takes about 1 second, and in the older version it took about 3.5 seconds. So this is a bit of a speed up. If you have interpolating the functions in one variable, you can use them much more efficiently in PDEs that are more than one variable. Okay, so one last slide about the future of PDE modeling. So in the next version, we hope to see more solid mechanics, so plastic deformation. We're working on axisymmetric fluid flow, and we're trying to investigate a bit of neural networks for PDE solving. Yeah, that's the things we're working on, and we'll see how far we get. So again, thanks for your attention. NDSolve rocks. I think it's the coolest function ever. Yeah, if you have questions, I think we'll now have a panel discussion, and you can ask questions there, or I'll see what else you've given in the chat. Right, thank you.
Thank you, Oliver. And I'll now request the other speakers to also join our panel discussion. So those are 3 wonderful talks, and you can see Mark here, Oliver is here, and I think that one thing to say over here is that we actually have a good release, but we also part of a much bigger release, and there's lots of other stuff that's worth looking at in 14.2. So I just strongly encourage you to actually look at those other parts of the release, and those actually do bring the point home that we are constantly evolving as a language, first of all, and people like myself really ought to pay more attention, because often we're doing these tasks like select all the time. Believe it or not, most of our code is actually written in Wolfram language these days. There's Tabel, of course, which will be covered next, other talks, and then we have machine learning. That's the first big piece, game theory for our team, mathematical computation, and we have GPU computation, another big new area, which, by the way, began as a problem with linear algebra, which I kind of helped initiate 3 years ago, long before the generative AI revolution. And then we have geometry, graphs and networks, etc. And then what we just heard Oliver speak about, PDE modeling, which I think looks like it's already invited a lot of very positive comments. So that's the summary for the release. Regarding today's webinar, I've always admired people. At one time, I admired people who were good speakers, because I wasn't much of a speaker myself. But then today I do a bit more speaking, and I really admire people who can listen carefully. So I've already seen some excellent questions from the audience. I still see a few more coming up, probably for Oliver. So we're happy to answer as many questions you like, for as long as you like. I think we answered most of the questions in good time. There was one question from Pavel about Arduino support. Well, I did use Mathematica and Arduino a long time ago. as not as a developer, not as a Wolfram, but as a parent, actually, I helped one of my kids use Arduino for an electrical engineering project. So even I'm not totally current. So we'll try and back up what we said today with more answers later on if required. But this is a good time now for me to ask the other speakers, just go around and ask them if they have any final thoughts and also answer any remaining questions orally. So maybe I'll let Oliver take a small break. He's just finished speaking. Mark, if you want to go ahead and give some final thoughts for today's webinar.
Yeah, sure. There was a question that was given in general, and I thought I should address it in voice. That there is a lot of I guess, literature that when you think of game theory, you will mostly think of war, of a nuclear deterrence. And although you can use game theory to analyze it, it was actually a discovery that was done after game theory was established and after the nuclear deterrence issues and conflicts. And so there's a few books that I could recommend on this, but mostly by Schleenwell, the book on strategy and war games is one of the foundational books for game theory. So yeah, I just wanted to address this little bit of tidbit. I know we have game theory is one of those areas that is a bit out there and a bit different than our PDEs and so on. But I think we can see from these presentations that we're moving toward the right direction and we're making progress in large fields of mathematics, and we hope to continue to do so. And we have a co-creator over here.
Thank you, Mark. That's okay. We have some more audience with you, obviously. And I'm used to it because I meet Mark quite often. So maybe Oliver is now ready to say a few words about the PDE modeling and where he thinks things stand. Go ahead, Oliver.
So, I mean, we've been working on PDE modeling for quite a few years by now, and I'm always keen to interact with people that that make use of it. I had many interactions with customers, and I thoroughly enjoy those. And many good ideas actually came from things customers wanted to solve. So if you have a preference for a specific field, drop me a line. I'll see how we can schedule that up and things like that. So we'll see. I mean, I enjoy interacting with customers, and if you're working on PDE modeling, feel free to contact me, and we'll see what we can do. Right.
Okay, I don't see Adam here. Adam, are you here by any chance?
Yeah, I'm here. I just don't have camera.
That's okay. Well, Adam, I think, is one of the people who works quietly, but he's the deepest probably of all of us. So it's always a pleasure to listen to him, and he doesn't make mistakes, as we all know. So, Adam, why don't you go ahead and give some thoughts about what you saw in terms of questions today, any thoughts that you have to offer. And meanwhile, I'll ask Oliver particularly and Mark to look at the questions that are coming in and see whether they can, respond to them. But Adam, please go ahead and share your thoughts.
So basically, what I would like to say is that the symbolic array functionality is still under development, and in particular, integrating with the tensor functions, it's still work in progress. So that's something that will hopefully happen in the future versions.
Maybe I can quickly chime in there too. So, I mean, maybe some people know that we have hyperelastic material models also for solid mechanics, and these are in principle heavy users of these array functions that Adam now did. And at some point in the future, we'll update them to use the new functionality that Adam now provided. So it's natural that some things in the system lag a little bit behind because I mean, PDE modeling is not entirely trivial. Not that the array functionality is trivial. I didn't want to say that, but it takes, even for us, it takes a little time to digest the new development and incorporate this into a new function. I myself, I'm really happy that we have this new functionality that Adam added there. So that's really cool.
Yes, I agree. And I think that we already had one suggestion for having a control systems functions use the new matrix symbols, etc. Because there are large systems of differential equations. You need a compact notation for the solutions, etc. And I think we now have the language to express larger problems. The problem with Mathematica has been, first of all, getting the compute power, solving large problems, then having the right language, the right modeling language. And although Adam may not think of it that way because he's got a more general framework in mind, we actually do have a lot of, kind of ideas for how to use what he's done for real world modeling. Okay, I'm going to ask Adam if he's got any other thoughts for now. And Oliver, I do see, if you want to comment at any of the questions that came because you spoke last, go ahead. Yeah. Adam, go ahead if you have any final thoughts before I hand back to Oliver.
I see one more question about implementing a cross product as matrix multiplication. So we sort of make a distinction between vectors and 1 by n arrays. So that's why it's not implemented this way. So that's what.
Okay. Thanks.
Other than that.
Yeah. Thanks, Oliver. Do you want to anything else that you want to answer?
Yeah. So Harold just asked whether there is a way to compute the force that are exerted on the magnets, and right now there is no built-in function for that, but that's actually a good suggestion to have something like that. And in fact, in other fields of physics, we do have that. So if you like post-processing functions, so if you want to compute the stress or strain from on solid mechanics objects, we should have something like this. Actually, that's a good idea to compute the force that are exerted on the magnets. Yeah, so we should have something like that.
Mark, any thoughts related to the questions that specific from today that you want to add before we start? Meanwhile, others, please do type questions into the chat if you still have questions. We are still waiting for you to answer.
Maybe I can
Sure.
go back to one of the earlier questions. So I've been asked whether it's possible to use GPUs for PDE solving, and the answer currently is no. And the reason is it's not as straightforward as putting some functions onto the GPU and then hoping for a speed up. So if you want to make an efficient use of GPUs, you have to do as much as you possibly can on the GPU and then get the result back off the GPU. So as little transfer to the GPU and from the GPU as possible. So the first thing, excuse me, the first thing we're going to see in this area is then probably that we need a function like linear solve to work on the GPU, because that is really at the core of PDE solving and many other things, of course. So once that is done, then we can start thinking about doing more stuff on the GPU. Yeah, but I Devendra, correct me, but I think we are working on GPU support for linear solve.
Yes, exactly. And yeah, go ahead. And that's where it all began, by the way. So we do already have some support for linear solve in GPUs, and it began with some other libraries which before the current storm from NVIDIA on the GPU side. There was this library called Magma. So we are aware of what's there. The problem with linear algebra, in a sense, is that it's already got to the point where speeding up more is hard. The individual people who we rely on for our linear algebra have already put in a lot of work. So going to the next level is hard because we were already very, very good. So yes, we are working on linear solve. I actually have a plot somewhere which shows that you can get speed ups, but it's the thing with this technology is that the answer is not an unconditional yes. You need to know a certain range of problems for which it works better, etc. So all the way, we are working on linear algebra for GPUs, and it will improve, and we'll of course involve FEM at the right stage. Okay, thanks. Mark, anything from you? Any thoughts?
Regarding two questions that passed by, a course on game theory, study group on game theory, those kinds of ideas are in the plans. That's something we would like to do. Mind you, this is not something we have started even, so it is in the plans, but it won't be very soon. But yeah, of course, we plan on growing this game theory functionality to even more than just Nash equilibria in terms of optimum. And so we plan to, this is like the first round for this new branch, and we plan to develop it more.
Thanks, Mark. And I think there are really two targets for the next couple of years. The first target is to get a course and a book and a study group on game theory. Once we have enough feedback from people like you about what more we need to do for this first round. So it's going to take some time to settle down game theory for the next release, and then we'll do the course and the book and the study group. And then beyond that, we want to do a second round of game theory, a little more high-powered for the professional economists, etc. I mean, game theory has won lots of Nobel Prize for people in economics. Doesn't mean that economies has necessarily benefit, but economics certainly has benefited. So I think I think it's one of those mathematical tools in the right hands that can have a lot of power. So yes, game theory is still on our agenda, but we want to hear from you before we do anything much more beyond the study group and the course. But thank you very much. It's nice when the suggestions come from you. Okay, Adam, anything else from you? Any other comments that you have?
Not at the moment, no.
Okay, so I think we're heading to the end. I still see a couple of questions coming in about, okay, so does implicit region work with line integrate in 14.2? Michelle, the answer is not right now. There are some issues with orientation, but I'm going to pass this along to Marcos Aragnes, who looks after this. In fact, we've been thinking about this. The difficulty with the implicit region is that you don't have an inherent orientation, but you might say that's an excuse, so we're going to work on it. Okay, but I definitely will push that a little bit more. It certainly helps to have that facility in line integrate. So that's a good suggestion. Thank you for confirming that you would like it. Okay, and right. So I think, okay, so we have another question from Carl Hahn, which about notation. Okay, right. Maybe you can explain a bit more, Carl, about what that the notation gap is. But I see, maybe it's already been answered. So, Adam, anyone, if you want to comment on those questions, that's fine. But I think that yes, notation is quite a bit of a problem in general for us. Like I mentioned, even the array notation is now valuable, but we need to make sure that it gets propagated everywhere. Okay, then I think we're heading. We deliberately kept the webinar a bit short to make sure that you have enough, but not too much of talking from us. So I'm going to close in a minute or two, unless we see lots of other questions coming in. Okay. So, oh, I see. The question is about from Carl. Maybe Mark can respond to that about bridging the notation gap of game theory.
Yeah, I think maybe to try to answer that, it's true that classical game theory, like how you see it in textbooks, uses lists, uses many different devices that is kind of difficult to express, let's say, very high multi-dimensional games. As soon as you break into at least 3 players, the usual textbook notation kind of breaks down. So we're trying to alleviate for that in our own ways. So I think there's a little bit of learning to do with our own functionality, but we think that our functionality actually allows for clearer representation of games, especially matrix games, than what you would see normally in the textbook. That said, I think we try to make the bridge as close as possible within our documentation. But of course, if you see problems or potential confusion in those different notations, you're free to let us know and we'll correct it.
Sure, absolutely. And I think that's the whole point, that I know the textbooks have a very different way of doing things sometimes, but I think we are not restricted 2x2 games, etc., etc. So our framework is a bit more general. we have looked at game theory. I should mention the reason for my interest in game theory was that it was the final chapter in the course on finite mathematics, and we didn't have the functionality, so I decided to do it. I haven't gone back, but definitely we should do that as well. So thank you, Carl, for all those questions. And right, I think this is a general problem. How do you go from a word problem to code? Well, that's exactly, I think, what the LLMs are trying to do. So the hope is that very soon we'll have a system whereby something like the notebook assistant can be used to generate the code required to solve a word problem. Wolfram Alpha already does that, but I think it's somewhat limited in language. It's a small language model. I think the large language models are much better at that. So my hope is that in the next 6 months or so, we'll challenge the LLMs to solve our word problems for us. If that works out, they are better equipped to do it. That's just my 2 cents on it. But I think maybe it's time for us to wrap up and pass back to Roberto to close the webinar. But thank you all very much for all these questions. Thank you to the speakers for a wonderful job today, to Lewis for answering questions. And I'm going to stop speaking so Roberto can have a chance to take over. Thank you.
Thank you.
Thank you.